Hello my friends, welcome to this course on artificial neural networks. We will cover it in less than 2 hours, that's our challenge. So the value of this course is twofold. First, we're going to implement an artificial neural network using TensorFlow 2, so the brand new TensorFlow. And second, we will implement it on the Google Colab platform, which is the best platform to code in Python and to code artificial intelligence or machine learning or deep learning, because indeed you won't have any worry about how to install packages. All the packages are already installed and you just have to import them to use them. So that's really amazing and it removes a lot of pain. So that's where we will all code together. So let's do this. Let's start. If you're ready, we're going to implement this step by step as usual from scratch. You will code everything with me. I really want you to take action and implement the code with me, at the same time so that you can really practice yourself at home. So let's do this. Here we go with the first step. So the first step is very simply to be introduced to the dataset. And the dataset, we're going to get it from a great platform of dataset, which is the UCI machine learning repository. So here on Google, we're all going to type UCI machine learning repository, this one. And then we're going to go to the first link, UCI machine learning repository. And if you don't know this, well, you should really, because this is a great platform to practice implementing machine learning, because you have a lot of data sets on which you can, try your machine learning or deep learning models. So this is the welcoming page. You have all the newest data sets here, the most popular data sets hit since 2007. Okay, but where we're going to go is here, view all data sets. So click this link here, and there you go. That's really what I wanted to show you. The UCI machine learning repository is clearly well organized between the different applications of machine learning, which are classification, regression, and clustering. So just to explain quickly, classification is a branch of machine learning where you're going to predict a category, for example, the winner of a football game or the next president of a country. Regression is the branch of machine learning where you predict a continuous outcome, a real value like the salary of a new employee or the temperature of tomorrow or the energy output of a system, any continuous real value. And then clustering is another branch of machine learning, which is actually called unsupervised, and which consists of identifying some patterns in the data. And it is called clustering because usually the patterns are in the form of clusters. We identify some clusters of data within a high-dimensional data set. You can see clusters also as segments of data grouped by similarities. So we won't cover clustering in this course because what we want to implement is an artificial neural network, and artificial neural networks are used for supervised learning, meaning that we know what to predict, and the artificial neural network we will build will be used for actually regression, which is another good thing about this course, because usually in our other machine learning or deep learning courses, we implement an artificial neural network for classification. And this time I wanted to make something new. I want to implement this for regression, meaning that we're going to predict a continuous real outcome. So here we're going to go to regression. In the default task, we're going to go to the regression category in order to find all the data sets for regression. So you have 112, therefore a lot of opportunities to practice. And the one we're interested in is this one, combined cycle power plant. Here we go. So let's click it and let's see what this is about. All right, so you have here all the dataset informations. Here you have all the main facts about this dataset. The fact that it is a multivariate dataset. Indeed, we will have several attributes here. These are the ones to predict our dependent variable, our continuous outcome, which is the net hourly electrical energy output. Then the attribute characteristics are real numbers, instead of integers, for example. The associated task is, of course, regression. It's a regression task. We're going to predict a continuous real outcome, the energy output in megawatt. Then the number of instances is 9,568, meaning that's the number of observations with which we're going to train our artificial neural network to understand the correlations between those attributes such as the temperature, the pressure, humidity, vacuum, and what we want to predict, meaning the energy output. Then the number of attributes is 4, meaning that we're going to use 4 features, which are these ones, temperature, pressure, humidity, and vacuum, to predict, once again, the energy output. Missing values, no, they're not missing values. That's good. We won't have to do any data pre-processing, which is good because since we only have 2 hours to cover ANN's artificial neural network, well, it's better that we really focus on this. The area is computer, okay. Date donated, okay, 2014. And number of web hits, okay. So these are the facts. And so, as you understood, our practical activity will simply consist of predicting the net hourly electrical energy output, which is a real number, thanks to 4 attributes or 4 features, which are these ones: the temperature, the pressure, the humidity, and the exhaust vacuum. Okay? So that's it. That's simple. It's a simple data set, but that's because, once again, I really want to focus on how to build the artificial neural network with TensorFlow 2. So now what we're going to do is move on to the second step. You don't have to download the dataset here from this website. I just wanted to show you this website to see where it comes from and also to see all the dataset information. But you don't have to download this because in the next tutorial, you will have a link to download this dataset. So you will have exactly the same dataset as mine. This is the same as this one, but at least, we'll have the same name of the dataset. And therefore, when we import it on Python, on our Colab notebook, well, you'll make sure to import it the right way. Okay? So first step done, we got introduced to the dataset. Now we're going to move on to the second step, which is to start our implementation. This is the whole implementation of the artificial neural network. And in the next tutorial, along with the dataset, you will also get the link of this notebook. So make sure to get it. However, when you're going to click the link, you will end up here on this notebook. However, it will only be in read-only mode. Therefore, you won't be able to do any modification. So what you will have to do, and let's do it now so that we can be ready to start already from the next tutorial, is we're going to click File here, and then we're going to click Save a Copy in Drive. And that way, we will be able to do some modifications and, especially implement our artificial neural network. Okay, and so final thing before we move on to step 2, we're going to delete all the code cells here because I really want us to re-implement this from scratch so that you can really code it yourself. It will stick better in your head, if you take action in code. So let's just remove all the cells here so that we can indeed re-implement it from scratch, step by step, until we get the final result. All right, so that's how you do it. Make sure to delete only the code cells and not the text cells. The text cells indeed highlight the structure of this implementation, so you want to make sure to keep them to know where we are going throughout the implementation. And there we go. So that's the whole structure of this implementation, which we will start in the next step. So as you can see, it's an implementation structured in 3 parts. Part 1, data preprocessing. Part 2, building the ANN. And part 3, training the ANN. And at the same time, we will predict the results of the test set, which will be created here in part 1, data preprocessing. So we're going to start easy. The first sub-step is to import the libraries. Indeed, we will need several libraries to build our artificial neural network. First, we will need the NumPy library because, of course, we will use with arrays, and the NumPy library is best to manipulate arrays. Then we're going to import the pandas library, which will be used for part 1, data preprocessing, when importing the dataset, but then we will split the dataset into a training set and test set with another library, which is scikit-learn. And then, of course, we will have to import TensorFlow because, as I've told you in the previous tutorial, this artificial neural network will be built with TensorFlow 2. So let's do this. Let's create a new code cell. You just have to click here, code cell, and let's import the libraries. Once again, I remind that the beauty of Google Colab is that we don't have to install any package because everything is already pre-installed, so that's really amazing. And therefore, we can just directly import the libraries. So here we go. The first library which we have to import, as we said, is NumPy. And to import the library, you just have to start with import here. Then you put the name of your library, which is NumPy. And then, just because we are going to be lazy and we want to implement fast, well, we always add a shortcut, which is NP, because whenever we want to use a library, we have to call it first, and it's better to call it with NP. You know, it's faster to call it with NP rather than NumPy. So to add this shortcut, we just need to add here as NP. All right, very simply. Then second library, as we said, is pandas. So pandas for data preprocessing, and same, we're gonna add a little shortcut here, which will be PD, much simpler. And finally, of course, we're going to import TensorFlow, and we're gonna add the shortcut TF, right? These are the classic shortcuts. You'll find them in every implementation. Import TensorFlow as TF, perfect. And now we're just going to make sure that indeed we're going to work with TensorFlow 2.0. So I'm going to create a new code cell here, and the trick to find this is to just run here tf._version and _ again. And as we can see, so we first have to run the cell to import the 3 libraries. So let's do this. You just have to click the play button here to run cell, and it is importing them. It's taking a little time. That's totally normal. It's because it's the first run, but then you're going to see that the future runs will be super fast. And now if we run the cell, what do we get? We get indeed TensorFlow 2, 2.2.0. So that's amazing. You will actually learn how to build an artificial neural network with the brand new TensorFlow. All right, so first step done. Now we're going to move on to part 1, data preprocessing, with the first sub-step, importing the dataset. You can already create a new code cell to be ready from the next tutorial. Now let's tackle part 1, data preprocessing. So the first thing we'll have to do is to import the dataset. You already downloaded it on your machine thanks to the link given in the previous tutorial, and now we'll have to import it within this notebook. So the first thing we have to do before importing it is to indeed upload it within Google Colab. So you just click this folder icon here, then you're going to click upload, and there you go. Well, it's already ready on my side. I actually put it in my desktop on the artificial neural network folder, and then I can just find it here. So you can just find it on your machine, then select it, and then click open, and this will be imported in Google Colab. Just click OK here. This is just a reminder that indeed we're running a notebook for a limited amount of time, which is 24 hours. But don't worry, our ANN will be built and trained in actually few seconds, maybe minutes for the training, but definitely less than 24 hours. So here is the dataset. Now it is uploaded on Google Colab, so we can import it here in this code cell. So let's do this. The first thing we'll have to do is to create a variable which will contain this dataset, in a Python structure, which is a data frame. So this new variable, we'll call it dataset because it will actually be nothing else than the dataset in the data frame format. And so this dataset will be equal to what will be returned by the pandas library, and more specifically, a function by the pandas library. This function is actually read_Excel, and it's called this way because it will read, the Excel dataset. It is an Excel format, not a CSV format. So it will read this dataset and import it to integrate it into this dataset variable. All right, so let's do this. Since this function is a function of the pandas library, well, first we'll have to call the pandas library. Remember that it has a shortcut PD, so here we can just call it by the PD shortcut. And then you need to add a dot to call the function. And as we said, the function we want to use by pandas is the following one, read_Excel. Here it is. That's the other beauty of Google Colab. It already helps you with all the tools and functions and classes that you're using. So then, since it is a function, you need to add some parentheses, and then you need to add some input. You have all the inputs here. They really help you well. But the only input we'll actually need is, of course, the name of our dataset. The read_Excel function has to know what to import. And this is exactly this Excel dataset. All right, so here we'll simply have to import in quotes the name of the dataset. So let's enter it here. Capital F, OLDS, folds 5x2. Not the best name of the dataset, but that's all right. _pp dot, you need to add the extension XLSX. And there we go. We are ready to import the dataset. However, that's not enough. Because when we work on machine learning, deep learning, artificial neural network, and we are about to train a machine learning model or a neural network on this dataset, well, we always have to create two separate subsets, which are first the matrix of features and second the dependent variable vector. So very simply, as you might have guessed, the matrix of features is just a subset of the dataset containing all the features, all the columns that contain features, and the dependent variable vector is just one single vector containing the variable which you want to predict, which is called the dependent variable. In other words, the matrix of features will contain all these features here, so the temperature, the pressure, the humidity, and the exhaust vacuum, and the dependent variable vector will only contain the output to predict, which is the net hourly electrical energy output. And that's what we always have to do when working with machine learning or building an artificial neural network. We have to create these two separate subsets. So let's do this. We're going to call it capital X for the matrix of features and lowercase y for the dependent variable vector. That's usually the notations we use to build such entities. All right, so first let's create the matrix of features X. And in order to do so, well, we're first going to call our data set because indeed X is a subset of the data set. And now we're simply going to play with the indexes to only select the columns corresponding to the matrix of features X, meaning the columns containing the features. All right, these columns here. Actually, I will show you in the end what we will have created. Okay, so data set, and as we said, we're going to play with the indexes, and to do so, we just need to add here .iloc. You can see it as a function of pandas because indeed dataset is a pandas object, and as any Python object, well, it has some attributes or functions that you can use, and the one we use right now is iloc to select with the indexes the columns we want to select. All right, so here we need to just add some brackets, and inside these brackets we will tell exactly what to select. Not only the columns but also the rows. And here we will actually start to select the rows and then the columns. So first, well, obviously we want all the rows. We want all the observations in our subset X, the matrix of features. And to select all the rows, the trick is to add some colon here. Indeed, what this means is that we're taking the range of all the rows from the first one up to the last one, but we don't have to specify the indexes. Then, comma, to now select the columns. And in order to select the columns, well, what we'll only have to do is select all the columns from the first one up to the one before last. We want to get the temperature, the pressure, the humidity, and the vacuum. These are the first columns of the array, first columns of the data set. And so we'll have to take all of them except the last one, meaning this one. That will be for the dependent variable vector. And the trick here to select all the columns is once again to use this colon which actually represents the range. And now you have to know something very important. A range in Python includes the lower bound but excludes the upper bound. And therefore here, that's the lower bound. We don't have to specify the index of that first column. But here, since we don't want the last column, well, we'll have to specify the upper bound. And remember this, the upper bound of a range is excluded. Therefore, what we only have to do here is to specify the index -1. That's exactly the index of the last column, -1. It's a trick in Python which allows you to access with the index the last column directly with -1 instead of, putting the exact index of the column, which would be, by the way, 0, 1, 2, 3, 4, right? That's another thing you need to know in Python. Indexes start at 0. Therefore, the first column here has index 0. This one, pressure, has index 1. Humidity has index 2. Vacuum has index 3. And this one, the energy output, has index 4. So you see, that's the trick. Instead of putting index 4 here, we put index -1, which is the index of the last column. And since the upper bound of the range is excluded, well, this will exclude the last column, and therefore we will take all the columns except the last one. And therefore we get all the features. You see the trick? That's a very good one to know in Python. And so now you know how to create a matrix of features, because indeed, usually most of the data set you will work with when building and training an artificial neural network or any machine learning model we'll actually have first the features in the first columns and the dependent variable to predict in the last column. So that's a very useful code to know. You can actually even use it as a template, but make sure that indeed you get the same format of the dataset. All right, and then we just have to add here dot values, because indeed we want to take all the values of these rows and these columns. Okay, so now I'm going to copy this exactly, because in order to create the dependent variable vector, well, we'll use exactly the same trick, iLock. But this time, actually try to guess what we'll have to replace here in order to get the last column, right? We want to get the dependent variable vector, which is the energy output, and therefore the last column of this dataset. And so try to guess, pause this video and take some time to guess. And now I'm going to tell you, well, obviously, since I explained that -1 represents the index of the last column, and we only want to get this time the last column, well, very simply, we just have to remove the range here, so that the column we're selecting here is only the last one. Not a range of columns, but only the last one, which has index indeed -1. And that's it. We're ready to get our dependent variable vector. So, perfect. We did 3 things here. First, we imported the dataset with pandas. Second, we created the matrix of features. And third, we created the dependent variable vector. So congratulations, that's a new step done. And now we're ready to move on to the next step, which will be to split the dataset into the training set and the test set. But let's not forget first to run the cell. Here we go. It is creating right now the dataset, the matrix of feature X, and the dependent variable vector Y. And now indeed, if we want to see what they look like, well, we can just print, for example, X, and also print Y, and you will see that they will be exactly the features and the dependent variable vector. So this is the matrix of features with here the first feature, the temperature, here the second feature, the pressure, here the humidity, and here the exhaust vacuum. And this is all the outputs, the outputs of the dataset, the energy output. And so, of course, then we're going to build the artificial neural network to understand the correlations between these features and the dependent variable output, the dependent variable vector. Okay? So congratulations. We can now move on to the next step. Here we go, splitting the data set into the training set and the test set. Are you ready for the next step? An easy one, splitting the data set into the training set and the test set. So let me quickly explain why we have to do this. That's simple. That's because we want to train separately our artificial neural network on a separate set called the training set, and we want to evaluate its performance on another separate set, which is called a test set. So we want to make that split in order to get these two separate sets. And this is actually very easy because we're going to do it with a great library for data science called scikit-learn. So it will only take 2 beautiful lines of code. So let's do this. Let's create a new code cell and let's split that data set into these 2 sets, training set and test set. All right, so first what we'll have to do is get the function we'll need to do so. That function is called train test split, and it's a function of indeed the scikit-learn library. But more specifically, it is a function of the model selection module in the scikit-learn library. The scikit-learn library is a huge library with many modules that complete different actions for different purposes, and one of these modules is called model selection. This is the module that allows you to compare different models or do some data preprocessing, just as what we're about to do. And indeed, this module contains the train test split function, which will allow us to split our data set into train set and a test set in a flashlight. All right, so let's do this. Let's first import our train test split function. This function is coming from, so that's why I'm starting with from here, the scikit-learn library, which is called sklearn here in Python. Then, in order to get access to another module, submodule, we need to add a dot here. Then, as we said, we want to access the model selection module, this one. And so from this model selection module, well, we're going to import the train test, should find it. Yes, there we go. Train test split function. All right, perfect. Now that we have this function, well, we're ready to split the dataset into the training set and test set. And so we're going to do that in Flashlight. Actually, you have to know how this function works. So it's a function that actually will take as input the dataset, but not in the form of the data frame, but in the form of the two subsets here, matrix of features X and dependent variable vector Y. So that will be the input, and it will return as output exactly what we want, meaning the training set and the test set, but still in the forms of X and Y. So it will actually return 4 outputs, which will be X train, the matrix of features of the training set, X test, the matrix of features of the test set, then Y train, the dependent variable vector of the training set, and Y test, the dependent variable vector of the test set. All right, so let's actually first create 4 new variables to indeed collect what will be returned by this train test split function. And as we've just said, what will be returned will be first the matrix of features of the training set, which we'll call X train, then second, the matrix of features of the test set, which we'll call X test, and third, the dependent variable vector of the training set, which we'll call Y train, and fourth, the dependent variable vector of the test set, which we'll call Y test. And then equal, because now we're about to get what will be returned by the train test split function. All right, perfect. So let's do this. Let's get that function, train test split. There we go. Since it is a function, I'm adding now some parentheses. And as we said, well, this function takes as input first the matrix of features X, and second, the dependent variable vector Y. And then we can add several inputs. The other inputs have default values, but here I always like to specify the test size we want, meaning the number of observations we'll put in the test set in percentage, and the percentage that I recommend is 20% or 25%, but not more, because we want to have enough data to train our artificial neural network on the training set. So here we're going to choose 0.2, and that means we will have 20% observations in the test set, meaning, remember, there are about 10,000 instances, meaning observations in the whole data set, and therefore, since here we're getting 20%, well, we will have a bit less than 2,000 observations in the test set, and therefore a bit less than 8,000 observations in the training set. So that will be way enough to train our artificial neural network in the training set, okay? And then one final argument which I would like to add, and this is just for the purpose of us working well together, it is random state. And that's actually a seed which will fix the randomness of, the train test split. Because when doing the split of the dataset between the training set and the test set, there will be some random factors happening. If you don't put random state and if you run this train test split function several times, you will get different splits of training set and test set. So I just want to add here random state equals 0 in order for us to have exactly the same split of training set and test set. That's not compulsory, but it's better if we have the same thing. All right, and that's it. There we go. With only 2 lines of code, and actually in a very short amount of time, we were able to split the dataset into the training set and the test set. Actually, let's do it by running the cell. And there we go. Now we have the training set and the test set, meaning the training set composed of X train and Y train, and the test set composed of X test and Y test. So, wow, now it's very exciting. We can move on to part 2, building the artificial neural network with, of course, TensorFlow 2, building the ANN. Congratulations for completing Part 1, data preprocessing. We indeed did a big part of the work because this is absolutely compulsory when it comes to building and training an artificial neural network on your dataset. So now we have the training set and test set ready, and we're ready to build the artificial neural network. And now the first step for us will be to discover the architecture of the artificial neural network we're going to build. And I've prepared it on a separate slide, which I'm going to give you in the whole folder of this course containing, the dataset, the implementation, and, well, this slide. So here is the artificial neural network we're about to build. You can recognize on the left the input layer containing the 4 features, the temperature, the pressure, the humidity, and the vacuum. So that's always the first layer, the input layer containing in different neurons each of the features. Then we're going to have a first hidden layer here with 6 hidden neurons. So that's, the green circles here represent the neurons. And then we're going to have a second hidden layer still containing 6 neurons, hidden neurons. And finally, we'll have the output layer containing, of course, 1 neuron, because we just have to predict 1 real value, which is the energy output. Remember, we're doing artificial neural network for regression. All right, so this is what we're going to build. We're going to build that, of course, with TensorFlow 2. You're going to see that it's going to be very, very easy. You can actually change the architecture if you'd like. And now, if some of you wonder, why do we choose such an architecture? Well, there's no rule of thumb. This is just a classic architecture which I've tried from my personal experience, and it turns out that this architecture will bring excellent results. You'll see that in the end. All right, so let's do this. Let's build this with TensorFlow 2. If you're ready, let's proceed. All right, so the first step, which is always the same first step when building an artificial neural network, is to initialize this ANN as a sequence of layers. You know, artificial neural networks have two types. The first type is a sequence of layers, and the second type is a computational graph. So here, as you can see, well, it is nothing else but a sequence of layers, with first the input layer, second the first hidden layer, third the second hidden layer, and finally the output layer. And therefore, here we have to introduce it as a sequence of layer. And so let's create a code cell here, a new code cell, and let me show you how to do this. All right, so the way to do this is by creating an object of the sequential class by TensorFlow. So as you understand, TensorFlow is like a deep learning library which allows you to build complex neural networks and train them with tools like optimizers or loss function or dropout tools, you know, many neural networks related tools. And one of these classes is actually the sequential class, which will exactly create an artificial neural network initialized as a sequence of layers. All right. So the first thing we're going to do here is create a new variable, which we'll call ANN, and this variable will represent exactly the artificial neural network we're about to build, okay? And this variable, what will it be exactly? Well, it will be exactly the object of the sequential class. If you don't know what a class is, you know, that's a very famous programming concept. A class is just an advanced computational structure which contains some variables and some actions, like some tools, you know. It contains what we call methods, which are like functions, which complete some operations or certain actions. And so this ANN object we're about to build will be indeed an object of the sequential class, and the sequential class contains indeed an ensemble of properties, variables, and actions, with all of which we're able to build an artificial neural network. All right? So now, as you might guess, I'm about to call the sequential class. However, this sequential class belongs to a certain module of TensorFlow called models, right? That's the name of the module. And this models module actually belongs to a sub-library of TensorFlow, which is Keras. Actually, before that, Keras and TensorFlow were separate. You know, these were separate libraries. But since the appearance of TensorFlow 2, Keras was actually integrated into TensorFlow. And that's why Keras has now become a sub-library of the whole TensorFlow library. And therefore, here, in order to call our sequential class, well, the first thing we have to do is, of course, to call the TensorFlow library, which, remembers, has the shortcut TF. Then from this TensorFlow library, we're going to call the Keras sub-library. And from this Keras sub-library, we're going to call this models module. And there we go. Now we can get access to this sequential class, you know, with a capital S, because that's a class. Classes always have the first letter as a capital letter, okay? So that's the sequential class, and just like a function, it has some parentheses, but we have nothing to input. And there you go. You created, let's say, the skeleton of your artificial neural network. Of course, then we still need to add the input layer, the first hidden layer, then the second hidden layer, and then the output layer. But at least we already introduced and initialized our artificial neural network as a sequence of layers as opposed to a computational graph. So that's the first step done. Congratulations, now you know how to initialize an artificial neural network using TensorFlow 2. That's excellent. So now let's move on to the next step, which will consist of adding the input layer, meaning this one, and the first hidden layer, meaning this one, containing 6 hidden neurons. And now we're about to add the different layers, starting with the input layer and the first hidden layer. So as a reminder, this is what we're going to build. And now in this new substep, we're about to create this input layer here of the 4 features: temperature, pressure, humidity, and vacuum, and the first hidden layer. Are you ready? Let's do this. So the first thing we have to do is, of course, to create a new code cell. And now we're about to, as I told you, use one of the operations or actions which you can use from the sequential class, right? I remind that a class in Python actually has a bunch of tools which you can use, and good news, one of these tools is the add function, which exactly is meant to add a layer within a neural network. All right, so now the question is, how do we use this add method? Well, that's very easy. We first need to take our object, ANN, and then we just add a dot, and that's where we call the action we want to use, which is the add action, but it is actually, technically a method, which you can see as a function within a class, and therefore we need to add here some parentheses, and in these parentheses we're going to add exactly the input layer and the first hidden layer. So how do we do this? Well, actually these layers will be created as actually an object of a new class, which is the dense class, and therefore the first thing we're going to input here is exactly that dense class. But this dense class, of course, belongs to a certain module from the Keras sublibrary by the TensorFlow library. So in order to access it, there we go, we need to follow a certain path, starting with, of course, TensorFlow, that's the whole library, from which we're going to get access to the Keras sublibrary, of course, from which we're going to get access to the layers module. So that's a different module than the previous one, that was the models module here, and now we're getting into the layers module, and from this layers module, well, there we go, we're going to call this dense class. Dense class, perfect, and some parentheses, of course, because this is a class. All right, so now I'm sure some of you wonder why is it called a dense class? Well, that stands for actually the connection between the input layer and the first hidden layer. Because indeed, as we can clearly see in this graphic, well, there is a full connection between the input layer here and the first hidden layer, meaning that all the neurons, which are here the features, are fully connected to all the hidden neurons here of the first hidden layer. And that's exactly what this dense class means. You can see the high density of the connections here. That's just what it means, okay? So the dense class will actually create these fully connected layers between the input layer and the first hidden layer. And so now the question is, what inputs do we need to enter here? Well, as you can see, they're all listed here. And that's the beauty of Google Colab. However, you can notice that there is a default value for most of the parameters. So fortunately, we won't have to input all of them. We will just keep the default value, except for two arguments, which are, of course, the first one, unit, and guess what unit is exactly? Well, that is nothing else than the number of hidden neurons in this first hidden layer. Indeed, we don't have to input the number of neurons in the first input layer because this will actually be recognized automatically by TensorFlow. Once we input the matrix of features later on to train the artificial neural network, it will automatically collect these 4 features. So we don't have to specify that there are 4 features. This will be automatically recognized by the neural network. However, we need to specify how many hidden neurons we want here for the first hidden layer, because there can be actually any number of hidden neurons, right? We are free to choose any architecture we want for our artificial neural network. So here we have to specify how many neurons we want in the first hidden layer, and that's exactly what this unit parameter is about. So here, first we will enter unit equals, of course, to 6, right? Because we want 6 hidden neurons in the first hidden layer. Then, next argument, so that's the only one we will have to change, compared to the default values here. We will keep all the other default values for the other parameters, but this one activation needs a specific, what we call an activation function. I remind that this is a free course and therefore, unfortunately, we can't spend too much time on this theory. However, the whole theory is provided in the course that is redirected at the end of this free course, and you'll understand everything about activation functions, but what you need to understand is that the activation functions we want to have for the full connections between the input layer and the first hidden layer is a rectifier activation function, which will just break the linearity of the operations happening between this input layer and the first hidden layer. That's what you must just remember now. And of course, this is all much more explained and much more detail in the long version of the neural network course, okay? So this is what we need to input here. Activation, there you go, equals, and the code name for the rectifier activation function, which you have to input in quotes, is the following relu. And that's it. As simply as that, this exactly adds the input layer and the first hidden layer to our neural network, so far only initialized as a sequence of layers. So you see that's really, really easy. And actually, it is so easy that in order to add the second hidden layer, which I'm going to do now because this is done in a flashlight, is just to copy this, you see, and just add it in a new code cell right here. And there you go, I've already added the second hidden layer. You see, this units parameter here is for the number of neurons, hidden neurons you want to have in your new hidden layer that you're adding. The first input layer is basically added automatically. Then the first hidden layer is added with the number of neurons specified in this units arguments here. And then same for the next layers, you just have to specify here in the units argument how many hidden neurons you want to have in this new hidden layer. And then the new hidden layer that you're adding is connected automatically to the previous one added before, you know, the first hidden layer. So actually, I just wanted to add a second hidden layer here just to show you how easy it is to add layers in a neural network you're building with TensorFlow. You actually don't have to add 2 hidden layers. It will work also very well with only 1 hidden layer, but now you know how to build a deep neural network, you know, with more than 1 hidden layers. So there we go. Now let's take a little break, and mostly I would like you to take action now on your own before I give you the solution. So what I would like you to do is to figure out how to add this last output layer, considering, of course, the architecture of the neural network introduced to you. So it's an easy one. There's no trap. Maybe there's a little trap which you'll have to be careful of, but it's okay if you fall into it, because even if you don't get the exact same solution as mine, I kind of suspect what you're going to bring up as a solution, it will actually still work. You will just get probably lower accuracy in the end, but it will still work and you'll still get good results. So try to do it on your own. Basically, you have all you need in order to add this final output layer, after which I will bring to you the solution. We will implement the end of part 2, building the ANN together, after which we will move on to part 3, training the ANN. All right, so how did you do? Did you manage to figure out how to add this output layer? Well, of course, the first thing you had to do was to copy this, right? Because it will be the same. We're still having some full connections between the second hidden layer and the output layer, in the sense that all the neurons of the second hidden layer are connected indeed to the final output neuron in the final output layer. So we still need a dense class to establish these full connections. However, there was something slightly different we needed to change inside the dense class. Let's see what this is. I'm going to paste that here. There we go. And obviously, the parameter which you had absolutely to change, you know, no matter what, is this unit parameter. Because indeed, this corresponds to the number of neurons you want to have in this new layer that you're adding. Right now, we're adding the output layer, and the output layer has only 1 neuron, and therefore, the units parameter here needs to be 1. So I hope everyone did that, right? Changed the units parameter from 6 to 1. But then the less obvious thing which had to be done is about the activation function. It's okay if you actually kept the rectifier activation function. It will still bring good results, as I said. But for the output layer, it is actually recommended to either have a sigmoid or a softmax activation function, or actually no activation function. But the sigmoid or softmax activation function is rather used for classification, whereas here we're doing regression. So actually, the thing that you had to do as a second change is to remove the activation function and keep it to none. You know, the default parameter, which is none, right? Remember, the activation function here has none as default parameter. So that was the second change, but it's totally okay if you did not make that change. This is actually known through experience. Now you know it. So remember this. Let's recap. If you're doing classification with only 2 categories to predict in the end, you know, either yes or no or 0 or 1, well, you have to choose a sigmoid activation function. If you're doing classification with more than 2 categories or classes to predict in the end, well, you should use a softmax activation function. And if you're doing regression, meaning that you have to predict a continuous real number as a final output, then you should choose no activation function. All right, try to remember this. And so now, congratulations, we are done with part 2, building the ANN. So we can move on to part 3, training the ANN, which we'll do in 3 parts. First, we'll compile the ANN, meaning that we will connect it to an optimizer, which will take care of reducing the loss during backward propagation and stochastic gradient descent. Then we'll have to choose also a loss function, all that when compiling the ANN. Then, of course, we will train the ANN model on the training set, of course. And finally, we will predict the results of the test set. So whenever you're ready, let's start part 3, training the ANN. So we'll tackle this part 3 in 3 sub-steps. The first one will be to compile the ANN with an optimizer and a loss function. The second sub-step will be to train the ANN model on the training set over a certain amount of epoch. And finally, we will predict the results of the test set. So let's do this, starting with the first sub-step, compiling the ANN. So first of all, before we forget, let's create a new code cell. And so this sub-step is about connecting to our artificial neural network an optimizer and a loss function. What is an optimizer and a loss function? Let me explain this to you right now on the graphic. So the optimizer is basically the tool with which you're going to perform stochastic gradient descent. What is stochastic gradient descent? Well, that's a technique that consists of updating the weights of each of the neurons in the hidden layers so as to reduce the loss over the epochs. In other words, what will happen is that first forward propagation will happen. The features will be entered into the neural network. The signal will be forward propagated up to the energy output. This energy output, meaning the prediction, will be compared to the real energy output of the training set. We have the real results. This will incur a loss, which will be exactly the squared difference between the predicted energy output and the real energy output. And usually the predictions come into batches so that we actually compute the sum of the squared differences between the predicted energy outputs and the real energy outputs in the batch. So basically you get a loss, and then backward propagation is applied, meaning that this loss is back propagated into the neural network, and stochastic gradient descent is applied with this optimizer to reduce the loss. So basically the optimizer will update all the weights inside this neural network in order to reduce this loss that was back propagated into the neural network. You see the idea? So you got the idea. Now let's indeed connect this artificial neural network to the optimizer and the loss function. And to do so, well, of course, we're going to use another one of these actions which we can get from the sequential class, right? Remember, this ANN, artificial neural network, is an object of the sequential class. And as with any classes in Python, you can use some operations, some functions, some actions from the class itself to complete some specific actions. And the one that we're about to use now is the compile method, right? The function within a class. So we're about to get our ANN object, from which we're going to call this compile method. It is a function, so I'm adding some parentheses. And let's see what we have to enter here. Usually Google Colab will tell. No, this time it doesn't want to tell. Okay, it's all right. So basically what you have to enter here is always the same. You have to enter, as I said, actually, an optimizer and a loss function. So there we go. Let's do this. The first parameter is named optimizer, right? And we will choose the classic Adam optimizer. This is the most popular optimizer when you want to perform stochastic gradient descent, which you should, because that's what will reduce the loss, meaning the difference basically between your predictions and the real results. So that's a highly recommended optimizer, and you can use this one by default anytime you want to train an artificial neural network, whether it is for regression or classification. And then the second parameter will be the loss. The loss will be, this time, be very careful, we are doing regression, and therefore the loss, as for any regression task, should be the mean squared error, or the root mean squared error. However, with TensorFlow, we're going to work with the mean squared error. Okay, so the mean squared error, as you might guess, and this is exactly what I've explained when, quickly explaining backpropagation and stochastic gradient descent with the use of the optimizer, the mean squared error is exactly the sum of the squared differences between the predictions and the real energy output in the batch, okay? And so let's enter this parameter in quotes, of course, and the exact name of this parameter is mean squared error. All right, and that's it. That's the only thing we had to do in order to compile our artificial neural network. So now that we have the optimizer and that we chose the right loss function, we are ready to train our artificial neural network on the training set using this time another method, which will be the fit method. And that's where we'll see exactly the training in action. You know, epoch by epoch, we will see actually the loss getting reduced. This will be very exciting. All right, let's do this. Are you ready for the training? Here we go, training the ANN model on the training set. So let's create a new code cell. And now, as I've told you at the end of the previous tutorial, in order to train this ANN model in the training set, we have to use another one of these actions which you can use from the sequential class, which is the fit method. So once again, we're going to take our ANN object with now all the input layer, hidden layers, and output layer, and also the optimizer and the loss function connected to it. So we're 100% ready for the training. Therefore, we're going to use this new method to train it. And this method is the fit method. Adding some parentheses here. And now, according to you, what do we have to input inside this fit method? Let's see if Google Colab can help us. No, that's all right. We can totally guess that. All right, so actually it's not that obvious. I mentioned the keyword, so if you paid close attention to what I said, you should be able to figure it out, but it's all right if you forget some of them. However, first there are two obvious ones. Can you guess what they are? Of course, these are X-train and Y-train, because indeed we have to train the ANN model on the training set, so we have to specify on which training set we want to fit the ANN, right? In other words, on which training set we want to train the ANN. And that's, of course, X-train and Y-train, and we have to specify these two elements separately. So first we have to enter X-train, basically the matrix of features of the training set, and then Y-train, the dependent variable vector of the training set, right? Remember, these contain all the features of the training set, and this dependent variable vector contains all the real results, all the real energy outputs of the dependent variable vector. All right, so Y-train, there we go. And now, can you guess what we have to input? If you have a little experience in deep learning and training artificial neural network, well, you might guess for sure that the next parameter we want to enter here is the number of epochs. Because indeed, you know what I've explained in the previous tutorial with the forward propagation first part of the process, and then the loss incurred, which is back propagated into the neural network, through which all the weights of the neurons will be updated in order to reduce that loss with this technique called stochastic gradient descent applied with our optimizer. Well, this actually happens over many epochs, and over each epoch the loss is slightly reduced. So we want to repeat this epochs in order to reduce more and more, little by little, that loss. So that's why we need a certain number of epochs, and that's exactly what we have to input here as the next parameter. So let's do this. The name of the parameter for that is epochs. And well, let's see. How many epochs do we want to use? How do we know that? Well, I actually had no idea before how many epochs it needed. So my pure reflex was just to choose 100 epochs. And indeed, this turned out to be a good number, because you will see that the loss will stop being reduced at around 50. So 50 would be okay, but in order to make sure that you converge when reducing the loss, you want to start with 100 epochs. And besides, you will see that it will be very fast, because indeed the dataset is small and not that complex, right? There are only 4 features. And then an optional parameter, which I would like to highlight here, even if it's not compulsory, because there is a default value, is the batch size. And usually we enter it before the epochs parameter. This is the parameter batch size, spelled this way, and we usually choose 32, meaning that, when I explained forward propagation and back propagation, well, the inputs, meaning the features that are forward propagated up to the energy output, usually come in a batch. So instead of forward propagating them one by one, we forward propagate them in batches of a certain number of elements, of a certain number of sets of these 4 features. And usually the classic batch size that we choose, by default, is 32. And then you can fine-tune your ANN by choosing some different batch sizes, but you will see that with this one, 32, we will get an excellent result. All right, and that's it. This is exactly what you need to input in this fit method. So now, congratulations, you know how to train an artificial neural network. And so now, without further ado, we're going to execute everything. I think that my notebook was disconnected, because Google Colab actually allows only 24 hours, I think, before restarting the runtime. So in order to make sure we restart from scratch, let's do this. You click runtime and then restart runtime here. Let's click yes. And now we're going to, re-execute each of the cells one by one until the training. This will be very exciting because we will finally see the training in action in the end, and we will see the loss getting reduced epoch by epoch, just as I explained. So let's go back. The Excel dataset is still here. You have to check that. And now here we go. Let's run the cells one by one. Starting with the first one, importing the libraries, then checking the TensorFlow version. Yes, we're working with TensorFlow 2. Then importing the dataset. Here we go into part 1, data preprocessing. The dataset is now imported. The matrix of features is created, as well as the dependent variable vector. We can print X and Y to have a quick look. All right. Then we split the dataset into the training set and test set. Now we go into part 2, building the ANN with this sequential class. So there we go. We initialize first the ANN. Then we add the input layer and the first hidden layer using the add method. Then we add the second hidden layer using the add method again, and the output layer using the add method again, but without an activation function. Don't forget that for regression. And now finally we're into part 3, and we first connect our ANN with an optimizer and a loss. That's what we call compiling the ANN. And now here we go. Are you ready? Let's run the training. And here we go. You can see the epochs going very fast, and the loss is here. Check the loss. So big loss at the beginning, then 230, 142 here at the 10th epoch, then 30, 29, 28, 27. So it's getting reduced little by little, and now it's starting to converge, The loss is almost not getting reduced anymore. And as I told you, yes, this was about epoch 50 that it started to converge. And at the end, epoch 100, still not finished. Yeah, there we go, epoch 100. We indeed end up with a loss at around 26, and it clearly converged because, as you can see, we start reaching actually the loss at around 26 at epoch 50, as I said. Okay, so there we go. Congratulations, the training is done now. I hope you got the same results and that you were excited as well to see that loss getting reduced over time. And so now we're gonna finally go from the training mode to what we call the inference mode, meaning that we're going to stop training our ANN. It is already trained, it is already smart, let's say, because it's an artificial brain, so that's why I'm saying it is already smart. And since it is already smart, well, we can use it to predict the results of new observations. And that's exactly what is contained in the test set. So that's our final step here. I just want to show you this last action from the sequential class, which you can use to predict some results of new observations. That method is called the predict method. So you can actually try to implement this first yourself before we do it together. So there you go. Please take action. Try to predict the results of the test set. There is actually absolutely no trap, so you can totally do it yourself. All right, let's do this. Let's implement that last step. I've already created a code cell actually, and that last step consists of predicting the results of the test set. Now, our artificial neural network is already trained. It was trained over 100 epoch, and the loss was clearly reduced down to around 26. So there we go. Now we're ready to go into inference mode, which consists of predicting results of new observations, which are exactly in the test set. So let's do this. I actually gave you a hint at the end of the previous tutorial. This new action that you have to use from the sequential class is the predict method, which consists exactly of predicting the results of any observations. Not necessarily new observations, but any observations. You could also use the predict method on the training set. But of course, that wouldn't be interesting because we know that our ANN was clearly and well trained on the training set, but now we want to test if it can also perform well on new observations in the test set. So let's do this. In order to call this predict method, let's not forget, of course, to take our object first, ANN, then this little dot here to call the method, and then here we go, predict. And this predict method, as any function, takes some input. And do you guess what they are? Oh, this time TensorFlow is helping us, so we clearly see what they are. That actually couldn't be more simple, because in order to predict the results of the test set, well, we simply have to input here the test set itself, but only, of course, the features, because that's what is fed into the neural network. And therefore, you probably very well guessed that the input we have to enter here is, of course, X test, right? Of course, because X test is exactly the matrix of features of the test set with which we're going to get through the predict method its predictions. All right, so first step done. So I suppose that you managed to implement this and then you run that cell, but you wanted to see the results, right? So if you run that cell, you will actually see the results being displayed here. But what I will do, and this is actually technical, so I did not expect to do that, what I will do is I will get all these predictions into a new vector which I'm going to call ypred, okay? So this is going to get all the predictions of the test set, and then I'm going to compare vertically, next to each other, ypred, the vector of prediction, to ytest, the vector of the real results, the real energy output of the test set, corresponding to xtest, so that we can see how well our model was able to perform on these new observations by, just comparing the predicted energy outputs and the real energy outputs next to each other. So now I'm going to do something quite technical. You don't have to understand it fully, even if I'm going to explain. First, I'm going to use NumPy to set the number of decimals after the comma in the predictions and the real results to 2. Otherwise, we'll get super huge number, with a large number of decimals after the comma, and this will be not very nice to see. So let me just do that quickly. I have to call NumPy first, which has a shortcut NP. Then I'm going to use this function by NumPy called set print options. This one, I'm glad Colab is helping me. Then parenthesis, and now Colab is helping me again. I just want to set that precision parameter to 2 so that we can indeed get only 2 figures after the comma, 2 decimals after the comma, okay? So precision here, yes, equals 2. Perfect. And now last step, I just want to put the 2 vectors of real energy outputs and predictions next to each other vertically so that we can clearly compare them together. All right, so now I'm going to do another technical thing. Remember that when we executed that cell here, printing X and Y, well, that's the matrix of features, that's fine, but the dependent variable vector Y was actually horizontal. And I would like to put it vertically so that we can compare ytest, meaning the dependent variable vector containing the real energy output, and ypred, the dependent variable vector containing the predicted energy output, vertically together. So what I'm going to do is reshape this vector, this horizontal vector, just to put it vertically. And the trick to do that in Python is to use the reshape function, and you're going to see the trick to do that. We first have to take the vector ypred, so I'm starting with ypred. I'm going to put ypred vertically. Then we add dot and then reshape, which is a function, so I'm adding some parentheses. And now I'm going to add 2 elements. The first one is the number of elements in ypred, which we can get with the len function this way, len ypred. And then the second one is 1. And by doing this, any horizontal vector that you reshape with these parameters here, first the number of elements in the vector and then 1, we'll just turn it from basically a matrix of 1 row and len ypred columns into a matrix of 1 column and len ypred rows. In other words, we're turning it from being horizontal to vertical, right? A good trick that you can know, even if, that's really not the most important here. Then I'm going to do the same for ytest, and then you'll see what I'm going to do, because now you might wonder how I'm going to put them vertically next to each other. So here I'm just doing the same for ytest. Ytest here. All right, so now with these 2 reshape, I've turned these vectors from being horizontal to vertical. Okay, good. Then, in order to put them next to each other vertically, I'm going to use another function by NumPy called the concatenate function. So here we go. It's a function by NumPy, so I'm calling NumPy first, which has the shortcut NP. Then from NumPy, I'm getting this concatenate function. There we go. I'm super glad Colab is helping me. And then some parentheses because it's a function, closing the parentheses on the other side. But then be careful. This concatenate function actually takes 2 arguments as input. The first one is the 2 vectors you want to concatenate into some parentheses. And that's the first element. Therefore, I'm adding some new parentheses here. So you see, I'm going to show you exactly. This is the first element, including the parentheses. That's the first element of the concatenate function, the first argument, right? And now, right here, I'm going to add the second argument, which is the axis along which you want to concatenate. And since we want to do a vertical concatenation, well, here we have to input 1. If we wanted to do a horizontal concatenation, it would be 0. All right, I hope it's clear. It might be very overwhelming at the beginning. My apologies for this. But, once you get the trick, you can just redo it very easily. And finally, well, what I would like to do is a little print, in order to print these 2 vectors concatenated together vertically. So very easy here. I just have to add the print function and close the parenthesis on the other side. So now let's hope I didn't make any mistake because this was quite technical. We're going to see that right away by running the cell, and I did not do any mistake. Perfect. All right, so first, you can see 2 vectors here, in the same matrix because they were concatenated together. This first vector here, this first column here is indeed the vector of predictions, ypred, which we got by calling the predict method on the test set features, xtest. And this second vertical column here is, of course, ytest, containing the real energy output of the test set. And so, in order to compare the predicted results to the real result, well, we have to compare each row one by one. And indeed, we beautifully observe that the predictions are each time very close to the real result, which is awesome, meaning that our artificial neural network performed super well, right? In the first example, the predicted energy output was 432 and the real energy output was 431. Then in the second observation, the predicted energy output was 463 and the real one was 460. Then 466, 461. So each time it's very close. And here, look at this one, almost the same. 473.85 for the predicted energy output and 473.26 for the real energy output. Then 440, 438, 459, 463. Well, that's just awesome. Our ANN was, remember, predicting new observations, meaning observations on which it wasn't trained. And here the predictions are very close to the real result. So that's an excellent performance. So congratulations, you made a very performant artificial neural network on this energy-related dataset. Now you know how to do data preprocessing and building an artificial neural network and then training it and also predicting new observations on the test set. So there you go. I hope you enjoyed this course. I really enjoyed making it for you. So I hope you enjoyed this course enough to feel the motivation and inspiration to proceed further. And until then, I wish you a great success in your scientific career and anyway in the future.